The topic is a bit different than the two previous talks. This is going to be more along the lines of, the session where James and Frank talked about, about sums of squares and semi-definite programming, and a particular application to computing something called the log-Sobolev inequalities. Okay, so I'm first going to talk a bit about the motivation, and then I'll talk about the techniques and so on. So the motivation really comes from Markov chains, the study of Markov chains. So we have a finite Markov chain. So we have a finite state space S. So that's just 1, 2, 3 up to n, let's say. And so we have a transition matrix. Okay, so this is a matrix that tells you the probability that if you're at node I, the probability of going to node J. Okay, so that's a non-negative number. And for each node I, you have to move to, the sum of the kij's has to be equal to 1, okay, because you have to move to one of the nodes. Okay, so that's what I call a transition matrix. So, so to any Markov chain, we associate, under some mild conditions, there's an invariant distribution, pi, so that's the distribution, so it's a vector in R to the S so you associate a probability to each node, and that's distribution, so that if you run the Markov chain one step, then the distribution the next step is the same as the distribution the current step. Okay, so so this means that pi j, so probability of being at j, is the same as the sum over all I, the other nodes I, of being in node I and then doing a transition from I to j, so that's pi I times kij. Okay, and so this equation can be written more succinctly as pi k is equal to pi. So this means that pi is a left eigenvector of k of eigenvalue 1. Okay, so under some mild conditions, such a pi exists, and I'm going to assume that such a pi exists. Okay, and so in the analysis of Markov chains, what we want to understand is if I start with an initial distribution that's different from the invariant distribution, and I run the Markov chain, I want to understand how fast does it converge to pi. Okay, so one can write down the discrete time Markov chain and the continuous time Markov chain. So here I wrote the continuous time one. It's called the Markov process usually. So P of t here is a vector in R to the S. It's a non-negative vector that sums to 1. And this is the equation, the continuous time equation that governs the idea of actually spreading, of running the Markov chain in continuous time. It's actually, it's really the heat equation if you want. And L here, it's a linear differential equation. And the matrix L that you see is identity minus K, and this is called the Laplacian. Okay. In the discrete time Markov chain would be that P at t plus 1 is equal to P of t times K. And this is the continuous time version. Often the continuous time is is easier to analyze than the discrete time one. Here I won't really be doing any analysis of Markov chains. Just in the next slide I will explain what are the kind of tools that people use to analyze such a continuous time Markov process. And then so this will lead me to define the so-called logarithmic Sobolev constant. And then from then on I won't be talking about Markov chains at all. Okay, so really the question is how fast does this P of t, the solution of this differential equation, converges to pi the stationary distribution. Okay, so this is a linear differential equation. So probably the first thing that comes to mind is to analyze the eigenvalues of L. Okay, and so this is kind of well known. I will just explain it in the way that's usually done in the Markov chain literature, and this will allow me to introduce the notation that will be needed to talk about the log-Sobolev inequality. Okay, so it may seem a bit unusual, if you're not familiar with this literature, but so what we kind of introduce is the density. So I want to study how P of t goes to pi. Okay, so I'm going to introduce the density of P of t with respect to pi, so that's just P of t divided by pi. And I want to study essentially how fast that x of t goes to 1, the vector of all ones. Okay, so x of t is going to the vector of all ones. Okay, so this means one way to capture how fast does it go to 1 is to study what we call the variance of x of t. Okay, so the variance of a constant vector of a constant random variable is equal to 0. So what we really want to understand is how fast does the variance of x of t goes to 0. Okay, and so the variance here is defined in this way more precisely. So it's the expected value with respect to the station distribution of x minus 1, and 1 here is that's the expected value of x of t. Okay. And so if you do simple calculations using the differential equation we have for P of t, you can show that the variance actually obeys a certain differential equation, which is that the derivative of the variance is equal to -2 times the quadratic form of the associated to the Laplacian evaluated at x of t. Okay, so that's so the bilinear form associated to the Laplacian is often called in the literature, the Dirichlet form. Okay, and so we have this this differential equation that governs how the variance of x of t evolves. And so now, if I would like to show that the variance goes to 0, the simplest way to do this is to try to find an inequality that will relate the right-hand side, E of x of t, to the variance of x, which is what I'm trying to study. Okay, and so this is precisely what is called the Poincaré inequality. So this is the fact that E of x, or E of xx, is bigger than or equal than lambda times the variance of x. Okay, so if you can prove such an inequality, then you plug that in your differential equation, and you get a differential inequality. Okay, and so standard results about differential inequalities will allow you to say that the variance of x of t actually goes to 0 with the rate minus lambda, so exponential -2 lambda t. And lambda here is the constant that you have in the inequality. Okay, and so by actually unpacking the definitions of E of x and the variance of x, it's actually quite easy to see that lambda is nothing but the second smallest eigenvalue of the Laplacian matrix. Okay, so this is related to the spectral gap. Okay, so and this tells us how fast the Markov chain so converges to the standard stationary distribution. Okay, so this is one way of measuring how fast does P of t goes to pi. Okay, but it's definitely not the only way. Okay, and so this is where the log-Sobolev inequality comes into play. So if I want to measure the distance from P of t to pi in a different way. Okay, so the log-Sobolev inequality has a similar form as the Poincaré inequality. So it's an inequality like this. So you want to lower bound also this term, this quadratic form, E of x associated to the Laplacian. But on the right-hand side, instead of having a variance, what you have is some entropic term. Okay, so you have a certain constant alpha that's going to be called the log-Sobolev constant. And you have a certain entropy, so entropy of x squared, and subject to, I mean, here we're restricting ourselves to the x's that lie on the sphere. Okay, so I won't really say where this is coming from, but the key fact here is that if you have such a log-Sobolev inequality, then you can show that the P of t, so this distribution in time, you can show convergence to pi in the relative entropy sense. So the relative entropy, or the KL divergence between two distributions, is given by this formula. So it's the sum of pi log of pi divided by qi. Okay, and so you can show, if you have such a log-Sobolev inequality, you can show that the divergence between P of t and pi is less than the initial divergence times exponential -4 alpha t. Now, why this is important, why we care about this? The reason is this can be actually sometimes can be much better than the variance, than the estimate based on the variance. Okay, especially especially the constant term in front of the exponential. Okay, so just to give you a kind of an idea, so let's assume that the initial distribution P of 0 is at Dirac, so you start at a certain node, and let's assume that pi is just the uniform distribution on my state space. Okay, then a simple calculation will tell you that the divergence between P of 0 and pi is the log of the size of the state space, whereas the variance of x of 0 is equal to the size of the state space. Okay, so you can see there's a really big difference between these two terms. And so that's why the estimate based on the relative entropy is sometimes much better, is sometimes what we're looking for really when analyzing these Markov chains. Okay, so, but okay, on the other hand, compared to, so lambda, which I said was just an eigenvalue, an eigenvalue computation, alpha is actually much harder to compute, as we can imagine. I mean, it's defined using this inequality. And so the kind of the purpose of this talk is to try to give some techniques, computational techniques, to compute alpha for a certain Markov chain. So you give me a transition matrix K, and I have an algorithm to give you a certified lower bound on alpha. Okay. And so, okay, so you can actually see this. So this is a screenshot from certain kind of well-known lecture notes on finite Markov chains that explains kind of tools, how to study mixing times of Markov chains. And the kind of, this is one question that was emphasized: how can one compute or estimate the constant alpha? And it says that it seems to be a very difficult problem. So, okay, so, and the technique that we'll use is based on sums of squares and so on. So I'll try to explain how we actually do this. Okay, so that was just the motivation really. And now I won't really be talking about Markov chains at all. I'll just be talking about, I want to prove a certain inequality. Yes, okay. So yeah, so maybe just a brief background, because I think the background of the audience is maybe a bit varied. So just a 2-slide kind of reminder of polynomial inequalities, sums of squares, and so on, semi-definite programming. So maybe let's forget a bit about log Sobolev inequalities. Let's assume I just want to decide. I have a decision question. I have 2 polynomials of with real coefficients, and I want to decide whether, let's say, P, the polynomial P, is non-negative for all x that satisfy Q is equal to 0. Okay, so in general, this decision question is difficult, it's hard. So a sufficient condition based on sums of squares is to try to express P, my polynomial P, as S of x plus a certain multiplier polynomial h of x times q of x, and where I require that the polynomial S is a sum of squares. Okay, so now this is a sufficient condition for this inequality to hold. Because if you take any x that satisfies q of x is equal to 0 and you plug it in the identity, this yellow identity, you get that P at this x is equal to S at this x. And so, and S of x is obviously non-negative because it's a sum of squares. And so I get that P is actually non-negative for all x such that q is equal to 0. Okay, so that's a sufficient condition. That's a way to prove it's a certificate for this blue question. So, okay, and what makes this sufficient condition interesting is that it's a tractable sufficient condition, in the sense that one can actually search for such a sum of squares proof efficiently using semi-definite programming, provided that you put a bound on the degree of S and H. Okay, so more precisely, if I let R of x to be the space of polynomials of degree less than D, okay, so a well-known result is that this a certain S, a polynomial S is a sum of squares if and only if there exists a symmetric matrix Q, and the size of Q is equal to the dimension of the space of polynomials in n variables of degree at most D over 2, such that Q is positive semi-definite, and such that certain linear constraints are satisfied. Okay, so this is not only linear in Q, but it's also linear in S, in the coefficients of S. So this actually allows me to search for such a polynomial S. Okay, so I can search for such a polynomial S, and then I have, these are linear constraints. The P of x is equal to S plus H times Q. these are linear constraints in my decision variables, so S and H. And so this is what we call a semi-definite program, okay? Because we have a positive semi-definite condition, and we have linear constraints. And so this gives us a semi-definite program that we could solve using any standard solver, or using actually the new solver of Frank based on geodesics. So I mean, yeah, or any other solver. Okay, so this is just a very brief kind of recap of sums of squares. So now, so we want to apply this. So this has been applied obviously to many problems involving polynomial inequalities. Now we want to apply this to our problem, but obviously the main difficulty is that we have a term that's not a polynomial. So if let me be more specific. So if I rewrite the log Sobolev inequality I want to prove in a way that matches what I have in my previous slide. So I want to show that I want to find an alpha such that E, this quadratic form associated to the Laplacian, minus alpha times B is this entropic term, is non-negative for all x that satisfy the sphere constraint. Okay. If B was a polynomial, then I could try to prove such an inequality using sums of squares, as I showed in the previous slide. But B here is not a polynomial. Okay, so I cannot really use sums of squares immediately. So how what do we do? Okay, so actually we're going to do something very simple. So we're just going to find a polynomial B hat that's an upper bound on B, and we're going to attempt to prove instead that like the stronger inequality, so that E of x minus alpha B hat of x is not negative for all x on the sphere. Okay, so this is going to be a stronger inequality because B hat is bigger than B. Okay, so obviously, and yeah, so we're going to try to prove this using sums of squares. So obviously the question is, how do I choose B hat? Okay, so what I'm going to do is I'm going to describe to you two approaches to do this. One approach is going to be, so I give you a certain fixed B hat and I prove to you that this B hat is actually bigger than B. I mean, you can see that B is a fixed polynomial, I mean, up to the choice of pi I. But we'll see that there is a fixed polynomial that's always an upper bound on B, and in fact, I'll give you a sequence of such polynomials. And the other approach is going to be based on a kind of slightly more advanced method, if you want, where actually the upper bound B hat is going to be a variable in the optimization problem, and in the sense that the optimization will actually look for the best upper bound that is suited for the Markov chain at hand that you're interested in. Okay, so I'm going to explain this. But the first approach, let me just explain the first approach, where we give just a fixed polynomial B hat. So so this is based on a very simple fact. It's an exercise really for first year undergrad. So you take the degree 2d minus 1 Taylor expansion of this function of t squared log t, which appears in here, right? And you can show that the odd degree Taylor expansion is always an upper bound. Okay, and so this means that B hat of x, which is just I mean the same as B, but where I replaced xi squared log xi by the Taylor expansion, this is going to be bigger than B of x. Okay, so this gives me a polynomial of degree 2d minus 1 in x. And what I can do is I can write down the sum of squares program to get a bound on the log Sobolev constant. So let me tell you more explicitly what this actually looks like. So we want to so this is really the key constraint here. So remember, this is my Dirichlet form or the Laplacian, and I want that this minus my B hat. So alpha hat B hat, so this is the expression you see. I want that this is equal to a certain sum of squares plus a multiplier polynomial times the sphere constraint. Okay, and so here H is, I mean, the variables of my optimization are really the sum of squares polynomial, H, and the alpha hat. Okay, And so you solve this SDP, and this will give you a formal lower bound on the log Sobolev constant. Okay. So in fact, this very simple approach already gives us some non-trivial results. So I mean, just to give you an example, I mean, one of the most famous, I mean, usually when you talk about log Sobolev inequalities, the first example you see is the so-called the 2-point space. So that's just a Markov chain on two nodes, where with probability 1/2 you stay at the current node, or with probability 1/2 you go to the other node. Okay, and it's known, one can compute it analytically, that the log Sobolev constant is 1/2 in this case. So in fact, this is kind of, even though it looks like a 2 example, this one is quite important, because one important property I didn't mention about the log Sobolev inequality is that it tensorizes, in the sense that if you computed the log Sobolev constant for a certain Markov chain, or for 2 Markov chains, let's say, then you can actually get the log Sobolev constant for the tensor product of the 2. I mean, there's a certain notion of tensor product of Markov chains, by just the log Sobolev constants of the small ones. And so by just computing this, the log Sobolev constant for the 2-point space, you can actually get the log Sobolev constant for for a Markov chain on the hypercube. Okay, and this is quite important. Okay, but anyway, so before, I mean, not talking about tensorization here, so the log Sobolev inequality we have to prove for the 2-point space. Kind of, if I write down everything, so I mean, if you unpack the definition of the Dirichlet form and then the B of x and so on, this is really what you want to show, this inequality. So if you use the Taylor expansion, the Taylor upper bound of degree 3, and again you replace everything, so replace the x squared log x by its Taylor upper bound, what this reduces to is to prove the following stronger inequality, okay, which is an inequality of degree 3, because I replace the x squared log x by a certain degree 3 polynomial. And so now I claim that this has a sum of squares proof, and actually it's very simple. So okay, this is the identity which you can verify by hand. Okay, so in this example, I cheated a little bit in that in order to have a simple example that I can put on the slide, I used some additional fact that one can use when proving these inequalities, is that one can assume that the x's are non-negative. So I actually use this fact, and I have this multiplier which is a non-negative. So okay, so this tells us that already the Taylor approach combined with the powerful sum of squares machinery allows us to get some non-trivial results on log Sobolev constants. Okay, so but in general, I mean, if you consider more general like Markov chains and so on, we want to find something that's a bit better than this. And so this is what the kind of the second approach is, the adaptive approach, where so now this is exactly the optimization problem I showed before, except that now I've left p hat to be a variable. Okay, so so before I put here p Taylor, now p hat is a variable of the optimization problem, and the constraint I put is that p hat is bigger than t squared log t for all t non-negative. Okay, so I mean, this optimization problem will allow you to search for the p hat. I mean, the upper bound that kind of is the best suited for this for the current Markov chain you're looking at. Okay, but obviously, so here there is a constraint in the optimization problem that's I mean, not so clear how to actually encode it using, let's say, semi-definite programming. And this is this constraint that p hat is bigger than t squared log t for all t. Okay, so it's a convex constraint because it's you have an infinite number of linear inequalities in p hat, but I need a tractable formulation for this constraint. Okay, so in other words, I have this convex set and this convex set of p hat, and I would like to have a formulation for it. So what I'm going to, the approach that we use for this is to use something, is to use actually also approximations of log, but this time rational approximations, which are much better than Taylor approximations. So let me maybe give a certain definition, also make a certain reminder. So this is a well-known notion from approximation theory, something called Padé approximation. So the mn, I mean, if you give me a function f of t and you give me two integers, or I mean, so okay, if you give me one integer, you can consider the Taylor approximation or the Taylor expansion up to degree n, let's say, of a function around a certain point. Now, if I give you two integer, one can consider the so-called the Padé approximation. Okay, and so this is a rational function, so p over q. So p is a polynomial of degree m and q is a polynomial of degree n. So that around t equal to t0, what you want is you want to match all the Taylor coefficients of f up to the maximum number of order, okay, up to the largest order. So you count how many degrees of freedom you have in p and q and so on. And so if things work well, I mean, generically, you're able to match up to m plus n coefficients. And so this means that f minus p over q is a big O of t minus t0 to the power m plus n plus 1. Okay, this is not always possible, but okay, let's, I mean, it's okay. Let's just assume that this is the case. So here I show you just a plot of the log function, which I'm interested in, and which is the one I'm interested in for the log Sobolev inequality. And so I plot the Taylor upper bound, okay, so of degree, I put of degree 7 in here, okay. So obviously it's equal to the log at the point 1. And I put the this Padé approximation of order 4-3, okay. So in fact, we don't even see the log function because the Padé completely, I mean, is almost equal to the log on this. I mean, yeah, in the plot, we cannot see the difference. So really, we see that the Padé approximation is much better than the Taylor approximation. In fact, we know that the Taylor doesn't even converge for, I mean, outside the radius of convergence, 1. So we see the divergence of the Taylor series outside of 1. Okay, so this is a Padé approximation. So there is a priori no guarantee that this is going to be a bound on the log function. Okay, and remember that really I'm interested in getting formal bounds on the log function. So, but actually it turns out that for the, I mean, again, for the log function here, a certain choice of Padé approximation guarantees that you get actually an upper bound. So if you choose the m plus 1 m, so meaning that the numerator has degree m plus 1 and the denominator has degree m, then you can guarantee that the Padé approximate of log is actually an upper bound on log. Okay, it's a formal upper bound. And okay, obviously there are it's defined, so it doesn't have any poles on the positive axis. Okay, so this is qm of t, you can choose it to be positive for all t positive. Okay, so now how do we exploit this fact? So remember, I'm interested in characterizing or in formulating the set of p hat of polynomials p hat that are bigger than t squared log t. Okay, so again, I'm going to kind of impose a certain stronger condition. So I'm going to impose that p hat is bigger than t squared times the rational approximation pm divided by qm. Okay, and now this I can impose using using sums of squares again by essentially clearing out qm. So p hat is bigger than t squared pm divided by qm if and only if qm times p hat minus t squared pm is not negative, and because here I'm working with univariate polynomials, this is equivalent to being a sum of squares. Yeah, so this is actually, I mean, in fact, we only need this to be an upper bound for t positive. So really, you want this to be a sum of squares plus, I mean, t plus, times the sum of squares. I mean, you put a multiplier with to only work on the positive axis. Okay, so once we have this, so we can actually now formulate again a sum of squares program or a semi-definite program that will give us again a lower bound on the log Sobolev constant. And now this time p hat is actually a variable in the optimization problem. So so it's exactly what I showed before, except that now in the last constraint we have that qm times p hat minus t squared times pm is a sum of squares. Okay, so there are really two parameters in this problem: the m, so the choice, the Padé approximate, and the degree of p hat. Okay, so obviously there is a relation between the two. You cannot choose them to be completely different, but you yeah, and obviously k as well. Okay, but k we actually always put the minimum value because the size of the SDP grows quite quickly with k. So okay, so yes, so this is the lower bound you can get using using semi-definite programming. So let me now mention kind of okay, so this you formulate a semi-definite program and you solve it using numerical solvers. This will give you an approximate, I mean, it will solve it using floating point numbers, but really ideally what I would like to get is a formal kind of mathematical lower bound on the log Sobolev constant with a certificate, okay, with a sum of squares certificate, okay, and not just something approximate. So this is so this requires additional kind of post-processing of the solution. So I'm going to briefly explain what we do. It's not okay. It's not terribly new. I mean, this is it uses I mean similar ideas that have been done before. So what happens is the semi-definite the sum of squares program I mentioned here is actually to solve it, we transform it into a semi-definite program in standard form. So okay, we have to construct a certain matrices AI and BI and a certain matrix C, such that the what we have the sum of squares program is equivalent to this formulation. Okay, so we take care when formulating the SDP to make sure that actually the SDP is strictly feasible. So this is quite important. So kind of we remove any yeah. So we kind of we simplify the sum of squares formulation in order to make sure that this is strictly feasible. And so the yeah. So in order to get a rational proof, what we really want is a rational X that satisfies the constraints of this SDP. Okay. Oops. Yes, and so getting such a thing from a numerical solution is not so easy because in general, let's say you get your X, and then you round it to a rational solution. So in general, the rounded solution will not satisfy the constraints exactly. So you project it on the subspace, let's say using exact arithmetic, but then you actually lose the positive semi-definite property. So so what we do in order to deal with this problem, again, we use the fact that we have a strictly feasible SDP. So we kind of perturb slightly the SDP and we require the X to be bigger than epsilon identity. And instead, this is the SDP that we give to the solver, to the floating point solver. And it is this X that we take and then we project on the subspace. And because we have a little bit of slack in the positive semi-definite constraint, the resulting the resulting matrix is still positive semi-definite. And one can actually do some quite, can get an estimate of what is the epsilon you have to put in here so that when you project, you get something that's still positive semi-definite. So this depends on kind of some norms and so on of the matrices AI. Okay, so this is all implemented in the Julia language. So my student Oisín did a very nice implementation of all this in the Julia language, and so yeah, so it's available on GitHub. So you can actually, so you just define your transition matrix K using, let's say, using rational numbers, and you call a certain function, you hit enter, and it will solve the SDP and it will do the rounding and so on. It will give you a rational lower bound on your log Sobolev constant. So let me briefly show you some examples. so here, so the default is that we use this Padé approach that I mentioned in the second part with m is equal to 5. Okay, and so this is an example where actually the log Sobolev constant is known analytically. So that's the complete graph. And then so from any node, you move to the neighbor node with probability 1 over n minus 1. So this has been computed analytically. And so we show that we get very, very good estimates. I mean, at least for not for moderate values of n using our approach. Again, so this is another example where we do not know the value analytically. What we do just to actually measure the gap is that we compute a lower bound using the SOS approach, and we compute an upper bound by running a local optimization method. So we use a quasi-Newton method to minimize the kind of the ratio of the Dirichlet form by this entropic term. And we actually get very small gaps. So this actually tells us also that the local heuristics often gives us the global optimum. So what you see, the plus here is the lower bound and the blue is the upper bound. Okay, and so now the last example, which is maybe the most important one, is that's the cycle graph. So this graph is the value of the log Sobolev constant is known for all n, for all even n. And it's conjectured that for all odd n, one should have the same formula, which is 1/2 of 1 minus cosine 2 pi over n. Okay, so there are very lengthy computations in this paper, Chen, Liu, Salov-Kost, to prove it for n equal to 5. Okay, so actually using our approach, we're able to prove this conjecture for n up to 21, essentially. So it's a computation proof. So we have formal certificates, but it's very large files. So that give you the sum of squares certificate, but there is a way to actually check. I mean, you have a small script that allows you to check that the proof is actually valid. So there are several ingredients to actually make this work. So we use the relaxation based on the Taylor upper bound of degree 5. We used obviously symmetry reduction. There are lots of symmetries in this problem to reduce the SDP block from something that's quadratic to something that's linear. And also something quite important is that because the alpha here is actually not rational, it involves this cosine term, we have to do all the rounding, all the exact arithmetic, not in the rationals, but in this number field in Q of cosine 2 pi over n. Okay, but my student was able to do all this and so on. So he got proofs for up to n equal 21. Okay, so now I just conclude. Yeah, so the paper is on the archive. There is kind of one interesting direction is to this question of finding the fastest mixing Markov chain, which is the question of if I give you like the sparsity pattern of the transition matrix, but I leave the actual the probabilities, you're allowed to choose them in such a way that the resulting transition matrix mixes as fast as possible. Okay, so if you choose, I mean, this question has been studied in this in this famous paper by Stephen Boyd, Percy Diaconis, and Lin Xiao in Siam Review. And so, I mean, the question really depends. How do we actually formulate the fastest mixing Markov chain? So in that paper, it's formulated as finding the Markov chain with the largest Poincaré constant. But another question that they also mention in that paper is to find the Markov chain with the largest log Sobolev constant. And a priori, this can give you kind of a different Markov chain, different optimal Markov chain. And so our formulation allows us to actually do this because the SDP we get depends linearly in the choice of the transition matrix. So the values in the transition matrix can also be variables in the optimization problem. So it would be interesting to actually do this comparison. Kind of one drawback is that our method is based on SDPs and it grows. I mean, they're quite big, so we cannot really scale this to very large graphs. Okay, and so there are other kind of open questions like to compute something called the modified log Sobolev constant and so on. But I think I'm over time, so I'm going to stop here. So thank you for your attention.
Thank you for the interesting talk, Hamza. Are there any questions?
Hi, Hamza.
Oh, hi, Diego. How are you doing?
I have a quick question.
Yeah.
Thank you for your talk. So Do you know anything about convergence of your lower bounds?
No, we don't know. We haven't proved anything. Yeah, it's actually a good question. We let's see. Maybe one can prove something about this one, because I think so. I mean, the Padé approximates, one can show that they converge to the log function, and then by taking, I mean, I think so. We have to let the different, different parameters go to infinity.
Yes.
So we have to let the degree of p hat. I mean, L and M, so they can go to infinity together, and K also has to go to infinity to get the and we use the like the fact that polynomials can strictly positive polynomials on the sphere can be written as sum of squares with large enough K. Maybe this can work. I do not know. We actually have not tried.
Okay.
That's a good question. Yeah. So,
okay. Thank you.
Yeah, you're welcome.
Any other questions?
Hamza, one question. Can you go again to slide 13? I think it was.
Yes. Yeah.
What you were showing. So in here, do you rescale things with the pi sub i's? The pi sub i's are fixed,
Yes,
right? So you could rescale this to the unit sphere, and it will actually be different, right? Because the approximation of the log will not actually be the same.
Yes, so to rescale, like you mean to change the Markov chain in such
No,
a way?
I'm saying just, I mean, in here formally just replace x sub I with x sub I divided by square root of pi sub I.
Oh, I see. Yes, actually, yes, you're right. Yeah, so maybe, yes, we have not tried this. And then so this upper bound will just be the sum over I of p hat of now yi or something.
Yeah, I think it's the same, I mean, somehow the same expression, but the point is approximation is going to be different.
Yes, yeah.
Right, because you're rescaling the domain.
That's right. Yes, yeah, you're right. We actually haven't tried this, but that's a good point.
Yeah. Because your approximation is good, I guess, around
around 1, yeah.
1, but what does 1 mean in there? 1 means
yes, so the xi is supposed to be the density. So so it's really the I mean, if we go back, I mean, to the original thing,
it's like a delta function, right? Like somehow, what in the case where you have it.
Yes. So let's see. So actually, 1, yes, is a point of singularity. I mean, if I remember, so is a point where this, I mean, these two things actually vanish. So this numerator, I mean, if I divide the e of x by the right hand side, this is a singularity, and so but yeah, and actually this is what is involved in proving actually that alpha is strictly positive, because it's not so trivial that actually the log Sobolev constant is strictly positive. You need to analyze exactly what happens. You need to do an expansion, I mean, to resolve essentially this singularity to show that alpha is strictly positive.
Right.
Yeah. But yeah, I mean, this rescaling idea, I mean, we haven't tried. I mean, we can see what.
I mean, maybe it makes a difference. I don't know. I mean, it's already super good, right? I mean, I think the errors that you get are like incredibly small. But yeah, great. Thank you.
Thanks a lot.
Any further questions?
Yeah, I have a question about the lower bound from the perturbation, where you perturb the semidefinite with so perturbing things. I guess you never know how much perturbation. I mean, if you have an ill-conditioned problem, a perturbation can result in a very large change in your objective. Why didn't you try to get a lower bound using the dual?
So, I mean, here it's important that we get a feasible point. So, I mean, this is, I mean, in a sense, this is already the dual. So we really want, yeah, so we really want a feasible point with a good value. That's enough for us. I mean, we don't really want to solve it to optimality. And so, I mean, we do this perturbation essentially to be able to then round to rationals and still maintain the positive semi-definiteness. This is, yeah.
So I'm sorry, I guess I missed it. So this is the dual of the problem?
Yeah, I mean, it's a dual in the sense that it's what we usually mean by a dual, that having a feasible point will give us a lower bound, right? So I mean, we actually don't have really to solve this to optimality. You give me any feasible point of this SDP, and this will give me a valid lower bound on the log Sobolev constant. We just want to find a good feasible point. Because it will give us a sum of squares. I mean, if I unpack, I mean, the definition of this SDP, this will give me a sum of squares proof and so on.
So why do you have to, I mean, if you got a strict feasible point and you're solving with a interior point method or something,
mm-hmm.
Aren't you getting the feasibility as you're?
Yeah, we are. I mean, it's total. Yeah, I mean, if we're okay with a floating point solution, then it's fine. But it's just a matter of, I mean, if I want to convince mathematician that I have a formal proof, and so he looks at my x and then he computes the smallest eigenvalues and he finds, I don't know, minus 10 to the power, I don't know, minus 10 or so. I mean, so I mean, maybe for some people this is okay, positive semi-definite, but we want something that's strictly, I mean, that's a sum of squares proof exactly. I mean,